We all know the correlation matrix from statistics or linear algebra, but have you considered what happens when you plot these matrices in space? Each entry in a correlation matrix ranges from -1 to 1 and quantifies the linear relationship between two variables. For example, height and weight are often positively correlated. As one increases, so does the other. A car's mileage and its second-hand price are negatively correlated. As mileage increases, the resale price decreases. The diagonal entries are always equal to 1 because each variable is perfectly correlated with itself. Here's an example with some specific values. Since a correlation matrix is symmetric and has 1s on the diagonal, it can be represented in three-dimensional space by mapping each of its upper or lower triangular entries to the x, y, or z axis. This gives us a point in 3D space. If we do this for more correlation matrices, we get more points. This leads to an interesting question. What is the shape of all 3x3 correlation matrices? Your first guess might be a cube centered at the origin with a side length of 2. This allows each correlation to range independently from -1 to 1. However, not every point in this cube is a valid correlation matrix because correlations constrain each other. Consider these 25 points that are not correlation matrices. Now, let me transform them into valid correlation matrices. What do you notice? Correlation matrices are restricted to a specific region within the cube, but what is the shape of this region? The missing piece is that correlation matrices are positive semi-definite. In this video, we won't focus on what this means, but treat it as a constraint a correlation matrix must satisfy. We can check this by verifying that the determinants of each submatrix, formed by removing matching rows and columns from the full matrix, are non-negative. For 3x3 matrices, the determinants of the first two submatrices always pass the test, so only the full determinant matters. Setting this to 0 defines the boundary for 3x3 correlation matrices. Does the resulting equation look familiar? If I adjust its form and simplify notation, holding z constant, you see it's a tilted ellipse. In fact, there is a different ellipse for each value of z between -1 and 1. You can take any xy point on or inside the ellipse and produce a 3x3 correlation matrix. But each ellipse tells only part of the story. It is a cross-section of the full three-dimensional shape. To see the full shape, we must layer these ellipses in 3 dimensions. This shape is called the elliptope. It defines the space of all 3x3 correlation matrices. Each of its 4 vertices represents a situation where all variables are perfectly correlated. In mathematical terms, these are rank 1 correlation matrices. The 1 in rank 1 means that data with this correlation structure live entirely in one dimension. For example, if you sample from a multivariate normal distribution with a rank 1 correlation matrix, every point falls exactly on a straight line. The elliptope has 6 edges connecting these vertices, forming a tetrahedral skeleton. Each point along an edge blends 2 of the rank 1 matrices and corresponds to a rank 2 correlation matrix. In fact, every point on the surface, apart from the four corners, is a rank 2 matrix. Data with a rank 2 correlation structure gain an additional direction of variability and lie on a plane. Points inside the elliptope are full-rank correlation matrices. These describe data that can freely spread out in all 3 dimensions. Additionally, the elliptope has 4 curved sides that vault outward over the triangular faces of the tetrahedron. To finish, let's look at the elliptope's volume. This is a neat mathematical result and helps build intuition about why correlation matrices are difficult to generate naively. If we first find the area of each ellipse, we can calculate the volume by adding them up using integration. The principal axis theorem helps here, since it lets us write the ellipses concisely as the sums of squared terms using eigenvalues and eigenvectors. Let's simplify the right side by dividing by 1 minus z squared, and rewrite the left side as a matrix multiplication. The middle matrix is symmetric and positive semi-definite, so we can break it into eigenvalues and orthonormal eigenvectors using matrix diagonalization. If we compute these multiplications from the outside in, the ellipse becomes the sum of 2 squared terms. These terms indicate the directions of its 2 axes, and their lengths relate to the eigenvalues. Check out this animation for a clearer picture. As you watch, notice that the larger the eigenvalue, the shorter the axis length. The expressions inside the squares are the projections of xy onto each eigenvector. The ellipse equation then scales these projections by the corresponding eigenvalues, meaning each projected coordinate can be at most the square root of the reciprocal of that eigenvalue. The beauty of this reformulation is that it allows us to transform the equation into the unit circle by a simple change of variables, producing a reflection combined with a non-uniform scaling. The area of each ellipse is now the integral over the unit disk of the absolute value of the determinant of the Jacobian. The area of any ellipse in the elliptope is pi divided by the square root of the product of its eigenvalues. Why does this make sense? Well, instead of multiplying pi by the radius squared, as we do for a circle, we multiply by the product of the axis lengths. Both eigenvalues depend on z, and simplify to the square root of 1 minus z squared. To calculate the volume of the elliptope, we integrate these areas over z, ranging from the bottom to the top of the elliptope. Turning the handle on the computation gives the result pi squared over 2. Now let's see why this is an interesting result from a probabilistic perspective. Remember earlier in the video, some samples from the cube were valid correlation matrices, but not all of them. What is the probability that a random sample from the cube is a correlation matrix? We can calculate this by taking the ratio of the volumes. Intuitively, the volume of the elliptope shows how much of the cube is positive semi-definite. Dividing this by the volume of the entire cube gives the probability that a matrix generated uniformly from the cube is a correlation matrix. This probability is pi squared over 16, or about 0.62. Here's an animation to complement this analysis. First, take 25 samples from the cube. Then, based on the determinant of the matrices constructed from them, color them. Teal for positive semi-definite matrices, orange otherwise. We can then examine the proportion of teal points relative to the total number of samples in each iteration. On average, this value should match our analytical result of pi squared over 16. By taking larger samples over more iterations, we build a sampling distribution with a mean that settles around our analytically derived value. So why was this important? Learning how the mathematical constraints on correlation matrices manifest in geometry helps us appreciate why they are challenging to generate. We are familiar with how distributions such as the normal distribution parameterize space, but not so confident with correlations. How would you parameterize this space? And what would you focus on? Sparsity? Approximate low-rank structure? There are many choices. This is why designing priors for correlation matrices is a challenge for Bayesian statisticians. Off-the-shelf solutions are helpful, but often the information you want to describe does not align with their expressive capabilities.